In some of the earlier videos, we've looked at firing the cannonballs vertically upwards. So let's say that we're going to fire this cannonball at velocity u. Okay, so your velocity time graph will look something like this. Hang on, velocity time graph, and it will be a diagonal line like this. Let's say the cannonball gets to its maximum height here. We're going to call this T max, time it takes to get to the maximum height. So that T max here is right here, okay? Because at this point here, the velocity. Remember, the velocity is up and down here. The velocity is zero. So this T max here is zero, and this bit here represents the time it takes to get to its maximum height. Okay, and this here represents the distance traveled. So the distance traveled on the way up equals the area of this thing here. Now, because we're on a flat plane, what happens is when you fire the cannonball will reach its maximum height, and it will free fall back down to Earth. Okay, so because this distance here going up is the same as the distance going down, then this area here will be exactly the same as this area here. If the two areas are the same, then this time here, the time it takes to get to maximum height, will equal the time it takes to free fall back down to Earth. And you can imagine it as like this. I don't know if you've been taught this in school, but you can imagine this as being two parallel lines. And when you draw a diagonal line across, the two angles are the same. Well, it turns out that this area will be the same as this area. If these two areas are the same, then this length here, the time length, if you like, the time length will equal this length here. Don't worry about it too much. Just accept that when you have a velocity time graph like this, this time here equals this time here, and in this scenario here, our velocity time graph terminates around here. It terminates here. Beyond this, it really has no meaning because the cannonball is on the ground. So the velocity time graph pretty much terminates around here. So because around here is the cannonball's on the ground, and before here you're going back in time. So this bit really has no meaning. So you're only interested in this bit here. But now look at this scenario here. We are going so you're on a cliff here, and we're going to fire the cannonball at velocity u. Okay, and as soon as the cannonball's fired, I'm going to retract the cannonball like this. Okay, so what happens is that you fire the cannonball, so it will shoot up like this. Okay, it will travel up here, and then as I'm after firing it, I'm going to retract this. So it will free fall back down to Earth again. But the thing is, it will fall down back to Earth, but then it will go beyond our starting position here. So this here we're going to say is zero. Remember, it's what's called arbitrary. I chose this arbitrarily. I can't say it, but this level here we chose it to be zero. I could choose down here to be zero, but for convenience I chose it to be here. It could be anywhere. I could choose zero to be here as our reference point, and then everything else will be negative. But we chose it to be here because it's convenient, because it's our starting. This cannon here is our starting position. So we're gonna call it zero there. Hang on, let me just put this back. Let me just restart this. Hang on. So we are here. Bear with me. And then so let's start again here. We're gonna fire this cannonball up. As soon as we fire it, we are going to retract the plank. Okay, and then the cannonball will free fall back down to Earth. Okay, but the thing is, what will our velocity time graph look like? So here, so your velocity time graph here, what will it look like? Previously it was just like this, and then pretty much it stops around here. This area is the same as this, but in this case here, your velocity time graph will look like this, diagonal line, but then it goes on for much longer. So this here is your u. So this is your u here, your initial velocity, and the gradient of this line here is really gravity, because in this example here we are on Earth, so this gradient will be minus, well, it should be 9.8, but let's round off to 10, minus 10. The gradient would be minus 10. Okay, now this is a straight line, so anytime you have a straight line in maths, it's going to be y equals mx plus c. Now this minus 10 goes into the m. Okay, and c here is the intercept, so it's u. But the important thing that I want to emphasize is that your T max is here. Always try and find the time it takes to get to maximum height. So your T max is here. Okay, T max. Oh, hang on. T max is here, and this area here represents the height of this thing. So it represents the maximum height, not T max, but the maximum height, and it will be in meters. T max will be in seconds. Okay, so this area here represents the height. But the thing is, on the way down here, if it takes T, well, if it takes T max to get to the maximum height, then this distance here will be 2 times T max. Okay, so this distance here. But the thing is, in our scenario here, it goes beyond. Well, this point here is this point here. But now, because we've got this cliff here, our velocity time graph will extend down here. Okay, so this area here represents the distance going down to here, and this area here represents the height of the cliff. So this whole height here represents, well, it's represented by the area of this big triangle here. Okay. In the next video, I will show you how you can find out the time it takes for the total flight time, so up and down. Okay.